Right, this is directly after I filmed that 1 hour computing video, so this may or may not hurt, but it's fine. We're doing particles, antiparticles, photons, particle interactions, classifications, and then quarks, antiquarks, conservation laws, leptons, decay. We'll see how far we get. We will probably get through it all. Let's be fully honest here. This is going to be animated and or whatever. Please sub. So I'm trying to get to 500 million billion. Antimatter. Antimatter is made out of particles. Every particle has an antiparticle. Antiparticles have the same mass and rest energy but are oppositely charged. That's very self-explanatory. So I'll explain using animation. Yay, this isn't exactly, well, it kind of is, but it isn't, but it is a subtle animation. So protons obviously has a charge of 1.6 times 10 to the minus 19, and electrons obviously have a charge of minus 1.6 times 10 to the minus 19. So that antiparticle, which is written conveniently like this, have a charge of minus 1.67 times 10 to the minus 19. And this one has a charge, an anti-electron is called a positron and has a charge of 1.6 times 10 to the minus 19. So it is literally opposites. Their mass is equal, but they are opposites. The antiparticles that you need to know of are antiprotons, positrons, antineutrinos, and antineutrons. So, what's the antiparticle of an electron? That is a positron. Yes, it is. So, antiparticles have the same mass and rest energy as their corresponding particles, but are oppositely charged. Obviously. So, photon models of electromagnetic radiation. So, electromagnetic radiation are little packets of energies. These energies, packets, we call photons. So, frequency and energy. So, the equation for energy is Planck's constant times frequency. So, Planck's constant is 6.63 times 10 to the minus 34. So, energy of different photons. Gamma obviously has the highest frequency because obviously gamma waves look like that, whereas radio waves look like that. So obviously the higher frequency helps out a lot more. So photon model, energy equals Planck's constant times frequency. So the energy of the photon is equal to Planck's constant times the frequency of the photon. Simple. So radio photons have the highest frequency. No, they don't. That's gamma photons, but we will read the whole thing. So they carry the most energy. Radio photons have the lowest frequency, so carry the least energy. There's obviously gamma. It goes gamma, X-ray, ultraviolet, visible light, infrared, microwaves, radio waves. So annihilation and pair production. So annihilation, this is when, okay, we'll do this as animated. Yay! Okay. This is when the particle and the antiparticle collide, and when they collide it makes a boom, and then after this it forms a pair of gamma photons. And the opposite to this is pair production, and pair production is when one gamma photon spontaneously turns into a particle antiparticle pair. Happiness. So the logistics of it is that the energy carried away by the gamma photon must equal the total energy of the particles to begin with, and each gamma photon must carry away at least the rest mass energy of one of the particles. And pair production, everything must be conserved basically. So when a particle and its corresponding antiparticle collide, they annihilate each other. Pair production is the opposite of annihilation. Pair production is when one high energy photon spontaneously turns into a particle-antiparticle pair. The energy of the photon must be at least the total kinetic energy of the particle-antiparticle pair it creates. Is when one high energy pair production is the opposite of annihilation. Yeah, pair production is when one high energy photon spontaneously turns into one particle-antiparticle pair. Yeah, the energy of particles. I feel it's not kinetic energy. I feel it's something else. Yeah, rest mass. Simple. What does this represent? Anti-neutrino. Anti-neutrino was discovered during beta decay because the beta decay mass was not conserved. So this is H. H is Planck's constant. This is 1220, and if we do some quick maths, this would be boom, bapped. Quick maths. What's the opposite of pair production? Annihilation. Annihilation. Simple. So look, I'll split this up into two. I'll split this up into this section and then the quarks into the next section. So the four fundamental forces. These are strong nuclear force, electromagnetic, weak nuclear, and gravity. So strong nuclear force. This is the thing that holds together the atoms of the proton and the neutron. It works at as optimum of about 5 femtometers. Is over 5 femtometers is when it will start working, and its optimum will be about 1. And then after 3, the electromagnetic force will become harder than it, thus making it so it just doesn't work and the electron breaks apart. So the graph looks kind of like this. Then it heavily does that. So this is 0.5 femtometers, where it like starts working. Below this, the protons repel. So at 1, it's at its optimum, and about 3, it starts getting too weak for it to actually work. So, electromagnetic force. The electromagnetic force is very strong and has a long range. It is responsible for interactions between charged objects like protons and electrons. Most everyday forces we experience are because of electromagnetic forces, e.g. touching. Weak nuclear force. This affects all types of particles. It's responsible for beta plus and beta minus decay, and it's very weak and for very short range forces. And gravity is what we experience. It's the weakest of the forces, and it's what keeps us planted to the ground or sucks us towards the center of the earth. What force is responsible for holding the nucleus of an atom together? Strong nuclear force. Fundamental forces, we know those. Exchange particles. So each fundamental part has its own exchange particle. These are called gauge bosons. Sure. So for the strong nuclear force, it's a gluon. For the electromagnetic force, it is the virtual photon. For gravity, it's a graviton. And for weak nuclear force is the Z plus, Z minus, Z plus, W plus double minus, Z0 bonsons. So I have fully done this off of memory, so that's why it's not in this order, but I am using this as revision as well. So, repulsion and attraction, I think you guys know what that is. Don't need to go over it. What is the exchange particle for electromagnetic force? So that is the virtual photon. So attraction is the thing that pulls two things together, and repulsion is the thing that pushes two things apart. So Feynman diagrams. We can represent particle interactions using Feynman diagrams. So the general rules are that the particle starts at the bottom and moves upwards. Particles have straight lines. Exchange particles have wiggly lines. Hard-ons left, leptons right. We'll come on to that next video, or maybe this one. Particles can't cross paths, and exchange particles. So, electromagnetic repulsion. So this is, if you look at this arrow here, this is when two electrons come and they repel because of the exchange particle. And this is a virtual photon. So W, that is obviously one of the weak nuclear force ones. So beta minus decay, as you see here, this is a neutron. So a neutron's coming in, a proton is shooting out, and it's making an electron and a neutrino and antineutrino. Beta plus decay. This is when a proton is becoming a neutron and a positron and a neutrino is formed. So beta minus is neutron becomes proton, sad electron and sad neutrino. Beta plus is when proton becomes a neutron and happy electron and happy neutrino. Electron capture. This is when a proton and electron come together and they make a neutron and a neutrino. An electron-proton collision. This is when an electron and a proton come together and they once again make a neutron and a neutrino. Simple. So, two electrons repel each other because of the electromagnetic force. The exchange particle is a virtual photon. Simple. So, hadrons on the left, leptons on the right. Yeah. So what force is responsible for the sensation of touch? E.g., when a tennis ball hits your hand. Electromagnetic force. Each fundamental force has its own exchange particle called bosons. So, what is produced after beta plus decay? So after beta plus decay, that is a happy one. So in that way, neutrons are produced, positrons are produced, and neutrinos are produced. Don't diss my way of doing it. It works. I've just done it. So electromagnetic force. Most everyday interactions, blah blah blah, touching it. Strong nuclear thing inside nucleus. Gravity holds us to the ground. Weak nuclear force does stuff such as beta minus beta plus decay. So W plus W minus ZO. Responsible for the strong nuclear force, that would be the bosons, that would be the gluon. And virtual photon would be responsible for the electromagnetic force. So, fundamental forces: strong, weak, electromagnetic, and gravity. Simple. And now we have, wait a second, does this, I really need to fix this, don't I? I really need to make it so you can actually, because some of the diagrams I draw you just can't see. What am I looking for? Yemen. Oh, that's a long way off, you know. Shout me for doing geography. Classification of particles. That's next. So, hadrons. Hadrons are protons and neutrons of particles that feel the strong nuclear force. Hadrons are made up of quarks that can be split into two categories: byrons and mesons. These are literally protons. They are like heavy duty protons that want to decay into protons. So byrons are hadrons which has three quarks. Protons and neutrons are both byrons. There are types of byrons that are found in cosmic rays, but you don't need to know them. And the proton is the only stable byron, so every byron will eventually become a proton, such as every lepton will eventually become an electron. Antibyrons. The antiparticle byrons are antibyrons. God damn it. So byron number. Byron number describes the amount of byrons present. So byrons have the byron number 1, antibyrons have the antibyron number -1. It is a quantum number, so it can only be an integer, and it is always conserved. Mesons. Mesons are hadrons that contain a quark and an antiquark. Examples are pions and kaons. Mesons can be found in cosmic rays and have a byron number of 0. I think pions actually decay into kaons. Pions versus kaons. Pions are the exchange particle for a strong nuclear force between nucleons. Kaons are more bigger and often decay into pions. I don't remember if that's what I said or not. Byron number of a proton is 1 because they are made up of protons. What type of hadron contain a quark and an antiquark? That would be a... what would it be? It would be a... well, it's not kaon and pion, so it has to be a meson. But it's not baron as well. So it has to be a meson, yeah. So, leptons. Leptons are fundamental particles, and so they can't be made any smaller. So kind of like quarks. So electrons and muons. Okay, so lepton number can be, okay, it's better to read this. The most common type of electron is the electron. There's another called the muon. Muons are more heavy duty electrons, so they eventually decay into electrons. Muons are negatively charged and are heavier, and are more unstable, so they decay into electrons. Neutrinos. Neutrinos are also leptons. Electrons and muons each have their own neutrino. The electron neutrino, VE, and the muon neutrino, V. Micro symbol. Neutrinos are almost massless particles with zero charge, so they don't do much, just they're used to justify beta minus decay. Lepton number. The lepton number describes the number of leptons. You get a different lepton number with each type of lepton. It must be conserved. So there's something else. So which of these particles are leptons? Yes, yes, electron. Simple. So what do muons decay into? Oh wait a second. That is not. Actually, wait, it is, isn't it? Yeah, I was right the first time. Why do you doubt yourself? So strangeness. Strangeness is a fundamental property of matter, like mass, charge, or Bion number, quantum number. Strangeness is a quantum number, so it can only take integer values. Strange quark has a strangeness of -1. An anti-strange quark has a strangeness of +1. Particles made from strange quarks have associated strangeness. Only strange quarks have a strangeness, the rest of them don't. And this is conserved. Unlike other quantum numbers, strangeness is only conserved in electromagnetic interactions. Nope, it's only conserved in strong interactions. I thought that was wrong. So explain why kaons are always produced in pairs. I'll let you do this. So 5, 4, 3, 2, 1, 0. So it's because kaons are produced via the strong interaction, strangeness is conserved, therefore it must always be in pairs. Simple. Easy. Done. Hadrons are defined as particles that feel the gravitational force. Nope, they feel the strong nuclear force. And what is the most common type of lepton? The electron. Because muons decay into electrons. If something interactions, such as kaon decay, something can change by -1. So in weak, strangeness can change. Simple. And now end of topic test. I should probably do this, give you time to write, do this, give you time to write, and do it like that. Sure. Which of these is not antimatter? 2, 1. Ooh, it's a neutrino. It's not antimatter. Sad times. I've got a TikTok like. Class. You can follow my TikTok if you want. What is the relative charge of an antiproton? 3, 2, 1. -1. So which of these statements are true? You can think about it, pause the video. 3, 2, 1. Antineutrinos have a relative charge of +1. No, they... Oh, antineutron. No, they don't. Antineutrino have more mass. Nope. Antineutrino have a relative charge of 0. Neutron have a relative charge of 0. Yes, they do. Neutrino has the same mass. Yes, they do. Positron has a relative charge of -1. Nope. It has a relative charge of +1. So what is the name of the constant H? 3, 2, 1. Planck's constant. I spelled Planck's wrong. Ah. So which photon has the most energy? 3, 2, yay. Gamma. Simple. So what is the correct equation for the energy of a photon? 3, 2, 1. Energy equals Planck's constant times frequency. So what happens when a particle and its antiparticle collide? 2, 1. Annihilation. Boom. 2 photons are gamma photons. What kind of photon? Oh wow, gamma. Amazing. So what is pair production? Pair. 2, 1. Production is the opposite of annihilation. Pair production is 1. High energy. 3, 2, 1. Photon spontaneously turns into particle-antiparticle pair. The energy of the photon must be the total 3, 2, 1. Rest. Mass energy of the particle-antiparticle pair it collides creates. Which force is the weakest? 2, 1. Gravity. Okay, I give up doing the 2, 1 thing. What force only affects hard-ons? Strong nuclear. That's because it's in the nucleus. There's a wham chicken, you know. What force acts on charged particles? Electromagnetic. Electromagnetic, yeah. So where these statements are true, exchange particles can push particles together. Forces cannot act instantaneously. Exchange particles and push particles apart. Yes, it can, because it was in the diagrams. Forces can act instantaneously. Exchange particles cannot push. It cannot push them together. Or it can push them together, and forces cannot act instantaneously, or can? They can. Oh Jesus. Yep. Where's the exchange particle of the strong nuclear force between quarks? Strong nuclear force between... Oh, gluon. Gluon. The other answer is pion. Whether these non-exchange particle for the weak nuclear force? Virtual photon. That is electromagnet. What are the two types of hard-on? They are Byron and Meson. Byron and Meson, yeah, because then there are lepton, muon, electron. Where these statements are true. Mesons have a quark and antiquark, yes they do. Byrons have 3 quarks, yes they do. And antineutrons have a Photon number of +1 or -1. Oh no 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 no. The antineutron have a Photon number of +1. Oh, for God's sake. It's so close though. Thanks baby raccoon. Thanks for watching. That was, I don't know what that was. That was particles of interaction. Peace.